Let me wrap up our little journey into the Kepler problem by discussing a few final concepts. What we're going to do in this video is derive Kepler's third law. We're going to analyze the energy of different orbits. We're also going to derive the Vis-Viva equation, and then we'll wrap it up with the Virial Theorem. Our main accomplishment in the previous video was showing that this inverse square law for gravitation implies that the orbit must be some sort of conic section. And the polar equation that we derived for the conic section was the following: that r, the radius, is equal to h squared over mu. Remember, h was the angular momentum per unit mass, mu was the gravitational parameter, divided by 1 plus e times cosine theta. And remember, e was the eccentricity. And depending on the value of the eccentricity, you get different sorts of conic sections. Now, also remember that this numerator, h squared over mu, we define that as p, so that we can rewrite this equation as p over 1 plus e times cosine theta. That p is a special parameter of the conic section called the semi-latus rectum. In this ellipse that I've drawn out here, the semi-latus rectum would be the distance from the origin, which is one focus of the ellipse, from the origin up here to the ellipse. So the distance from here to here would be p, the semi-latus rectum. This is semi-latus rectum because the full latus rectum would be the distance from here to here. So distance from here to here is p. Same thing with distance from here to here, that's also p. Now, by analyzing this polar equation a bit further, we can also find some other parameters of this ellipse. Now, I'll remind you too that the distance from here, the origin, to here on the x-axis, that can be found by plugging in theta equals 0. When we do that, we get p over 1 plus e times cosine of 0. So we get p over 1 plus e. So that means the distance from here to here is going to be p over 1 plus e. That's that distance. And similarly, if we plug in theta is equal to pi, we can find the distance from here to here on the x-axis. And if we do that, we'll get p over 1 minus e. Now, if we have the distance from here to here, also the distance from here to here, we can find the total distance from here to here. And for ellipses, that's called the major axis. So let's find that major axis. So let's just add p over 1 minus e to p over 1 plus e. You see the common denominator is 1 minus e times 1 plus e. Then the numerator is going to be p times 1 plus e plus p times 1 minus e. Distributing the numerator, we get p plus ep plus p minus ep. Then downstairs, we get 1 minus e squared. Notice that the ep and minus ep cancel. So what we get is 2p over 1 minus e squared. So that's the distance from here to here, the major axis. Now, the parameter that people often talk about is the semi-major axis, which is actually going to be 1/2 this value. So 1/2 this value, which I'm going to define as the semi-major axis A, is just going to be p over 1 minus e squared. So it's 1/2 the distance from here to here. And to draw that out in a bit more detail, we can also draw on the center of the ellipse, and the semi-major axis would be the distance from here to here, which we found is equal to a, which is p over 1 minus e squared. So here I've updated our ellipse to show the semi-major axis, which is the semi-latus rectum p over 1 minus e squared. Now, in addition to the major axis, this long axis here, we also have a minor axis, which is going to be this vertical distance here with respect to the center. So it's going to be the vertical distance from the maximal y value down here to the minimal y value. Now, you can actually derive a very similar equation for the semi-minor axis b, which will be the distance from, actually let me draw that in here. It's going to be that distance, which I'll call b. You can actually show this is equal to p over the square root of 1 minus e squared. And let me just sketch out how you would actually show that. And one hint I'll give you is that the angle corresponding to that maximal y value there, which is going to be this angle here, which we'll call alpha. This angle alpha is going to be the cosine inverse of minus e, the eccentricity. And you can do a bit of trigonometry to show that this semi-minor axis b is going to be p over the square root of 1 minus e squared. So let me label that here. The semi-minor axis, that's p over the square root of 1 minus e squared. So these are some important parameters of the ellipse. We've got 3 so far, just to review. We have the semi-latus rectum here. We have the semi-major axis here. And we have the semi-minor axis. Now you'll see that analyzing the ellipse in this detail is going to make proving Kepler's third law quite simple. Now what I'm going to do next is rearrange the furniture in these two equations. What I'm going to do up here is solve for 1 minus e squared. So 1 minus e squared, that's going to be equal to p over a. Down here I'm going to solve for the square root of 1 minus e squared. So the square root of 1 minus e squared, that's going to be equal to p over b. Just doing a little algebra over here. Now what I'm going to do in the second equation is square both sides. So squaring the left hand side just gives me 1 minus e squared. Squaring the right hand side gives me p squared over b squared. Now notice that this equation and this equation are both being set equal to 1 minus e squared. So I'm going to set the right hand sides equal to each other. So I have that p over a is equal to p squared over b squared. Now what I can do is I can cancel out one of those p's. So I'm left with 1 over a is equal to p over b squared. And finally, I can cross multiply here, and I can say that AP is equal to b squared. So this is actually a pretty pleasant equation, since it relates all those 3 parameters of the ellipse. So it's saying that the product of the semi-major axis and the semi-latus rectum is equal to the square of the semi-minor axis. So a pretty nice equation. And we're going to use this to prove Kepler's third law. Now let's actually derive Kepler's third law. And to do that, let's first go back to our ellipse. Remember that at the origin, we had one focus of the ellipse, and that's where m1 is going to be over time. And let's say I start off m2, the mass that's actually following this orbit, over here on the x-axis. Now over time, let's say m2 moves from here to here, we're going to start sweeping out some area. And then Kepler's second law is saying that that area, the rate of change of that area, is equal to a constant. And we've shown in the first video that that constant is 1/2 the angular momentum per unit mass. So this is that equal times implies equal areas law. So what we're going to do now is ask over one period, that is, when m2 starts here, goes all the way around and back, that's going to be one period. Over one period, how much area is swept out? Well, that's going to be the total area of this ellipse, which, by a well-known formula, that's equal to pi times a, the semi-major axis, times b, the semi-minor axis. So that's just a formula we get from pure geometry. The formula we get from Kepler's second law, since this is equal to a constant, namely 1/2 h, if I multiply this constant by the period, which I'm going to call big T, I get another expression for the total amount of area. So the total amount of area swept out over one period is going to be 1/2 h times big T. And big T is going to be that orbital period. Now the first manipulation I'm going to do is multiply both sides by 2. So on the left hand side I get 2 pi times AB is equal to h big T. Now the second thing I'm going to do is square both sides. So I'm going to get 4 pi squared a squared times b squared times h squared times t squared. Now, why did I do that? Because I'm going to make 2 substitutions now. The first one is going to be for b squared. Right there, I'm going to substitute b squared is equal to a times p. So on the left-hand side, I'm going to get 4 pi squared a squared times ap. I'm going to combine those a's together. That'll give me 4 pi squared times a cubed times p. And now on the right hand side, I'm going to make a substitution for h squared. And that's going to come from this equation here, which I'm going to rewrite as h squared is equal to mu times p. Just doing a little rearranging there. So I'm going to make that substitution for h squared. And on the right hand side, I get mu times p times big T squared. Now look what we've got going on here. We're going to cancel out those p's. So I'm left with mu times t squared, just writing this right hand side and on the left hand side now, is equal to, let's see what's left here, 4 pi squared a cubed. So 4 pi squared a cubed. And now let me divide both sides by mu, that way I can solve for t squared. So our final equation is saying that t squared is equal to 4 pi squared over mu times a cubed. So this is the statement of Kepler's third law, that the square of the orbital period is proportional to the cube of the semi-major axis. And you might see this written sometimes as t squared is proportional to a cubed. Or equivalently, you can say that the period is proportional to the semi-major axis a to the 3/2 power. So you can see that's a quite simple derivation of Kepler's third law, just doing a little analysis of the ellipse and using what we know about the semi-lattice rectum, which we derived from the previous video, and also Kepler's second law. So Kepler's third law was one major topic I wanted to talk about in this video, and the other one was an analysis of the energy of different orbital types. So let's go back to semi-elliptical orbit, where mass 1 is at one focus of the ellipse. Let me put mass 2 over there. What we were talking about in the previous video, in our discussion of conserved quantities, is that there was this conserved vector quantity, which is called c, or the Laplace vector, which is the same for mass 2 at any point in its orbit. And we were saying that this vector c has got to point along the major axis, so it's got to be a horizontally directed vector in this picture, and it's going to point either to the left or to the right, or 0. It's going to point toward the point of closest approach of mass 2. So this conserved vector, the Laplace vector, is going to look something like this in this picture. So that would be the vector c. If mass 2 moves over here, that vector stays the same. Same direction, same magnitude. So as mass 2 moves around, there's this little vector called c that's attached to it, and it stays the same throughout its orbit. Now, another way we can write this vector c is as mu times this vector e, the eccentricity vector. And I think I briefly mentioned this in the previous video. So since it's a scalar multiple, c and e are scalar multiples of one another, they're both going to point in the same direction, except the magnitude of this vector e, the magnitude is just going to be the eccentricity of the orbit. So pretty simple. And now what we're going to do is we're going to derive an expression, an equation for the energy of an orbit, depending on the parameters of the ellipse, depending on the angular momentum and the gravitational parameter. And what we're going to do is we're going to return to this polar equation, and I'm going to back this up one step. What I'm going to do is look at this denominator. I'm going to keep the numerator the same, h squared over mu. What I'm going to do is I'm going to rewrite this e times cosine theta as the dot product of the eccentricity vector dotted with r hat. Now, hopefully you can see that this is the same as this. If you just expand this out, e dot r is going to be the magnitude of e, which I call little e, times the magnitude of r hat, which is it's a unit vector, so it's 1, and then times cosine theta. Now, with this equation, r is equal to h squared over mu over 1 plus e dot r. I'm going to do a little bit of rearranging. I'm going to solve for this dot product here. What I'm going to do is I'm going to swap this with this. I get 1 plus e dot r hat is equal to h squared over mu times r, just doing a little bit of algebraic rearrangement. Then to solve for e dot r, just subtract 1 from both sides. So this is saying that the dot product is going to be equal to h squared over mu r minus 1. So I'm going to keep that in the back of my mind. We're going to substitute that in for a later step, as we'll see. Now the next thing I'm going to do is I'm going to rewrite this equation up here So I have h times r dot minus mu times r hat is equal to mu times e. Now remember what these things are. H was that angular momentum per unit mass by vector. R dot was the velocity vector, and r hat was that unit displacement vector. Now what I'm going to do is I'm going to move this quantity minus mu r hat to the right hand side. So I have h r dot is equal to mu times e plus r hat, also factoring out that mu. Now the next little trick I'm going to do is square both sides of this equation. So on the left hand side I have h r dot squared, and then on the right hand side I have mu squared times e plus r hat all squared. So just squaring both sides there. Now if you work through this on the left hand side, actually expand this thing out, you'll find that the left hand side is equal to little h squared. Little h is the magnitude of the area in that bivector, little h squared, times v squared, where v is the magnitude of the velocity, the magnitude of the vector r dot. So it's just as you would expect, h squared times v squared for the left hand side. And now for the right hand side, we're going to have to be a little bit careful. We're going to have to actually expand this stuff out. So I have mu squared. The first term when I square this is going to be e squared. The next one is going to be e times r hat. The next is going to be r hat times e. And the last one is going to be r hat squared. Now, remember what happens when you square a vector under the geometric product? E squared is going to be the magnitude of that vector, which I was just calling the scalar e squared. And then over here, we have r hat squared. What's the magnitude of r hat? That was a unit vector, so it's just going to be 1. So I've got those two terms taken care of. Now these middle two terms, these are a special collection of terms. Now, let me remind you, when we have a geometric product, and we have something that looks like this, uv plus vu, we have this special equation that actually 1/2 this thing is equal to the dot product between u and v. So you see here we're missing this 1/2, so it means that this thing that we're actually seeing is twice the dot product between e and r. So this thing is actually 2 times e dot r. So this is why I actually found what this dot product is down here, because I'm now going to make that substitution. I'll leave that mu squared alone for now. We still have that e squared, and then we have twice the dot product. So let me make the substitution here. We have 2 times h squared over mu r minus 2 plus 1. And of course, I'm going to simplify this. Minus 2 plus 1. It's going to be minus 1 over there. I'm also going to distribute the mu squared. So I'm going to have mu squared times e squared. When I distribute the mu squared, I'm going to have 1 cancellation right there. I'm going to be left with 1 copy of mu in the numerator. So I'm going to have 2 h squared mu over r. Then finally, I have that minus 1 there, but also the mu squared there. The mu squared. And that's still equal to h squared times v squared. So I've just relocated that equation up here. Now the next little thing I'm going to do is I'm going to move this term, this 2h squared mu over r, to the left hand side. So I'm going to have h squared times v squared minus 2 h squared mu over r is equal to these two remaining terms. I'm also going to pull out that mu squared again. It's going to be mu squared times e squared minus 1. And next I'm going to divide both sides by h squared, just to get rid of that h squared there. So on the left hand side I have this pretty suggestive expression, v squared minus 2 times mu over r is equal to mu squared over h squared times e squared minus 1. Now let's check out this left hand side. Now this looks pretty familiar. this almost looks like a kinetic energy term. This looks almost like a potential energy term, except it's actually 2 times that. Remember, the kinetic energy was per unit mass was 1/2 v squared, and then the potential energy per unit mass was minus mu over r, but we have that extra 2 there, and we have that 1 there instead of 1/2. So this is actually 2 times the total energy per unit mass, which in the previous videos I've been calling big E. So we have that 2 times the total energy is equal to mu squared over h squared. And actually what I'm going to do here is I'm going to yank out a minus sign and rewrite this as 1 minus e squared. And then the last little manipulation I'll do is just say that the total energy E is equal to minus mu squared over 2h squared times 1 minus e squared. Now let's analyze this equation a bit further and see how the total energy depends upon the eccentricity. Remember, we had that number line in the previous video for the different values of the eccentricity. We had this one special value when the eccentricity is exactly 0. That's when we have a circular orbit. We also had another special value when the eccentricity is exactly 1. That was the parabolic orbit. And in between here, in between 0 and 1, we had the usual case where you have an elliptic orbit. And then above 1, you have the hyperbolus. When we have a circular orbit, we're going to have that eccentricity being exactly 0. So let's plug in E equals 0 into this equation. And we're going to find that the total energy, big E, is going to be minus mu squared over 2h squared. So we see that the total energy is a negative number, first of all, and we see that's a very specific negative number. And if you look at the elliptical case, E is going to be between 0 and 1, so that means that 1 minus e squared is going to be a positive number. So a positive number times a negative number. So that means that for the elliptical cases, and the circle is a special case of the elliptical case, the total energy is going to be negative. So notice that for the 2 bounded orbits, because parabolas and hyperbolas, those are just going to go off, those are going to escape orbits, the 2 bounded orbits are going to have a total energy which is negative. Now, as you may expect, the parabolic orbit, which remember we were saying that's the special case of where it just escapes being an elliptic orbit, if you plug in E is equal to 1 in this equation, you have 1 minus 1, which is 0. And we see that for the parabola, the total energy is exactly 0. So this is just that threshold where it has just enough energy to escape orbit, as opposed to having not enough energy where it just comes back around and forms a very eccentric elliptical orbit. So that's the parabolic case. Then finally we have our hyperbolas. And the only remaining case is that the energy is positive. And you can see that if you plug in a value of E, which is above 1, you're going to get a negative number here. So negative number times a negative number is going to be a positive number. So the total energy is going to be above 0. So these two cases, where the energies are non-negative, you're going to have orbits which are not bounded, the parabolas and the hyperbolas. Now this equation for the total energy is already pretty compact, but I'd like to play around with this a little bit more just to show you how we can rewrite it as an even more compact equation. So what I'm going to do is I'm going to go back to h squared. Remember we had this other equation that the semi-lattice rectum P is equal to h squared over mu. That's what we derived in part 2 when we derived the polar equation for the orbit. So that, again, that means that h squared is equal to mu times P. And I'm going to substitute that h squared down there. So I'm going to get that minus mu squared over 2 times mu p, and then I have that factor of 1 minus e squared. So I'm going to cancel out one copy of the mu's, so I'm left with minus mu over 2 times p times 1 minus e squared. Now I'd like to focus on this 1 minus e squared over p thing for a second, because remember we had this other equation relating the semi-lattice rectum and the semi-major axis. And that equation was P is equal to A times 1 minus E squared. Now, if I rearrange this, I can show that 1 minus E squared over P is equal to 1 over A. Because you can see if I cross multiply this equation, I just get back to this equation. So I have 1 minus E squared over P is equal to 1 over A. So I'm going to make that substitution. And finally, I get that this is equal to minus mu over 2 times A. That's still equal to the total energy. So this is another pretty nice equation, saying that the total energy is minus the gravitational parameter over 2 times the semi-major axis. Now I'm going to actually use this variant of the energy equation to show the last two topics that I'd like to cover in this video, the Vis-Viva equation and the Virial Theorem. So first let's tackle this Vis-Viva equation. Let me show you what that is. So we have the total energy written as an expression involving the gravitational parameter and the semi-major axis. Let's recall that the total energy is a sum of kinetic and potential energies. So we have the kinetic, which I call T, plus U, which is that potential energy. That's equal to minus mu over 2A. These are actually the energies per unit mass. The kinetic energy per unit mass was just 1/2 V squared. And then the potential energy per unit mass was minus mu over R. And that's still equal to minus mu over 2A. And the Vis-Viva equation is going to be solved in terms of V squared. So I'm going to just solve for that term. So the first thing I'm going to do is bring this minus mu over R to the right-hand side. So I have 1/2 V squared is equal to mu over R minus mu over 2A. And then I'm going to multiply both sides by 2. So I get that V squared is equal to 2 mu over R minus mu over A. I get that cancellation with that 2 down there. And the last step is to factor out that mu. So I have the V squared is equal to mu times 2 over R minus 1 over A. And this is called the Vis-Viva equation. One neat aspect of the Vis-Viva equation that I shamelessly yanked from Wikipedia is that it gives a quick way of deriving the escape velocity equation. Now, if you want to escape an orbit, you want to let the semi-major axis go to infinity. Because if it's any finite value, you're just going to have a very elongated elliptic orbit. So what you want to do is let A go to infinity. So if A goes to infinity, that means 1 over A is going to go to 0. So that means that this term is going to disappear. And what you're going to be left with is simply V squared is equal to mu times 2 over R. So 2 mu over R. And just taking the square root of both sides, we have the escape velocity, which I'll write V sub E, is equal to the square root of 2 mu over R. Which is the same expression that you would get from a normal physics class where you consider the balance between kinetic and potential energies. You want to have that kinetic energy be just enough to counteract that potential energy. The last concept I'd like to cover using this equation for the total energy is the Virial Theorem. So let's consider the case where we have a perfectly circular orbit. So let's say that's our circular orbit. There's the center of the circle. Now, what is this semi-major axis going to be for the circular orbit? Well, that's the distance from the center to the circle right there. That's going to be the semi-major axis. But notice that's the same damn thing as the radius of the circle, or the radius of the orbit. So I'm just going to go ahead and set A equal to R in this equation. So I get that the total energy is minus mu over 2 times R. And as we have the circular orbit, of course, this R is going to be a constant. Now let me rewrite this in a more suggestive fashion. The total energy is going to be 1/2 times mu over R. Now what is this thing minus mu over R? That's that very special quantity, which we've been talking about. That's the potential energy per unit mass. So we actually find that the total energy is equal to 1/2 the potential energy. So that's a pretty neat finding. And let's go a little bit further with this. recall that the total energy is the sum of kinetic energy, T, plus a potential energy, U. What I'm going to do is I'm going to subtract U from both sides. And what I get is that the kinetic energy, T, is going to be equal to minus 1/2 the potential energy, just from 1/2 U minus U. And this statement here, that the kinetic energy is minus 1/2 the potential energy, is what's called the Virial Theorem. Now, for a circular orbit, this statement is true at all points during the orbit. Now, let's consider the case of where we have an elliptical orbit. So let's say that's our ellipse. Let's say that's the center of the ellipse, and our semi-major axis is going to be that thing right there. Now, of course, we're going to have one focus of the ellipse, and as the planet swings around here, it's going to speed up when it's over here. And this statement is not going to be true at every instant during the orbit. It's only true at every instant during the circular orbit. But in this case of the elliptic orbit, a related statement is true, in that the time average of the kinetic energy, which I'm going to denote with these brackets here, the time average of the kinetic energy is equal to minus 1/2 the time average of the potential energy. So this related statement for the elliptic orbit has to do with the averages of the kinetic and potential energy, because as that planet moves around, these two values are going to be changing. But if you consider the average, this related statement, which is also called the Virial Theorem, is going to be true. So this is a pretty neat, also pretty neat abstract finding too. It shows up in a few other places in physics. Let me actually give you a numerical example for this Virial Theorem. So let's suppose we have one of these circular orbits, and we consider an actual value for the potential energy. Let's say the potential energy is minus 10. Now, from this equation here, the total energy is 1/2 this potential energy. So that means the total energy is going to have to be minus 5. But then we have from this equation that the kinetic energy is minus 1/2 of the potential energy. So that means that the kinetic energy is going to be plus 5. So you can see that if we know one of these three quantities, and we know it's a circular orbit, you can actually compute the other two. So hopefully you've enjoyed this little excursion into one of the big achievements in physics, which is understanding how this inverse square law gives rise to conic sections as orbits, and how much you can already understand with your knowledge of 2D geometric algebra. And we're going to develop this further in future videos. We're going to push into 3 dimensions, probably even higher. So hopefully stay tuned for that. So as always, leave your angry comments below. If you enjoy the content, subscribe to my channel. And I'd like to thank all of you math nerds out there for 1,500 subscribers. Good Lord. Thanks for watching.